Hello and welcome back to Let's Code Physics. Today's episode is going to be a little bit different. I'm not going to be doing any programming in this episode because I could use some help. Last time when we were working on our enemy ship controls for black hole battles, I set up these two R values surrounding a black hole to where if the ship is outside of the outer circle, so if it's in this, large outer region out here, then the ship is going to thrust back toward the black hole because then it's getting away from the action. It's probably away from the player. If the ship is within this small region, if it's within R1, then it's going to be thrusting away from the black hole because then it's risking falling in. And if the ship is in this comfortable region between R1 and R2, then it's going to be coasting. I called these R min want and R max want, but those are long to write on a screen. So we're just going to call them R1 for the lesser one and R2 for the greater one. And what I want to do today is show you the algebra that I've worked out so far for what these two should be, because I seem to be missing something. I might not be missing something. It might be that there's no more information to be found, but I want to show you what I've got so far, because if there's something I'm missing, I would love to have it pointed out to me. Please let me know in the comments below if there is something that I am overlooking in this scenario. So what I've got so far is, this is basically a boundary value problem, right? So you've got two boundaries. You've got a boundary at ship position equals R1 and a boundary at ship position equals R2. So the way I'm thinking about this is, let's suppose the ship starts within the R1 region and it needs to get up to some special speed here at R1. So the sort of minimal condition you would need there at 0.1. Oh, my stylus is not working today. Not happy about that. There we go. At R equals R1. Not an N, Brian. Come on. There we go. At R equals R1, let's say the velocity needs to be some special value. So that's one of our unknowns, is V at R1. That's one unknown. And sort of to have sort of the minimal condition there, if the ship were to no longer be accelerating at that point, you would have the thrust pointing outward needs to cancel out the forces that are pulling it back toward the black hole. That would be the drag force, which we've set up as linear in V, plus the gravitational force G, mass of the black hole, mass of the ship, divided by R1 squared. Okay, so there's one equation and one unknown, and two unknowns, because we've got the V0 here and we've got R1 here. Okay, the second piece would be at R equals R2. So this would be the ship has successfully coasted through the coasting region and is now sitting at this sweet spot here where it's going to start to turn around. And so the minimal condition for that would be for it to just barely arrive there with a speed of 0. And so for that to work out, we've got to think about the ship going from this boundary to this boundary. And so we've got to set up that its final speed equals its initial speed plus an integral of the net force dt. Okay? Wonderfully vague, wonderfully generic, but we can set a few things on this. For example, this V we just said was 0, so we can go ahead and get rid of that guy. And then this F net is a little bit simpler than the force up here because there's no thrust acting in the coasting region. And so we've got the negative of the damping coefficient times the velocity, plus we've got, that's going to be a minus because it's pulling backward, minus the gravitational force GMM over now R2 squared. which is pretty great, except that this is a function of velocity, and this is a function of position. Both of these things are functions of time, but I don't know what their functions of time are. I'm pretty sure this is an unsolvable differential equation. I'm 99% sure about that. If there is a solution to this differential equation, definitely let me know, because that would be that would make this job a lot easier. But what we can do is we can take this dt and convert it to a dx if we were to multiply by dt over dx, which is a funny looking thing until you look at it upside down and realize this is position. It's time divided by position instead of position over time. So this is position over time inverted. So that's literally 1 divided by the velocity dx, which works out pretty well, because then this equation becomes 0 equals v naught. So there's one of our unknowns, plus integral of f net. So we're taking our negative bv minus gmm over r2 squared times this new form of dt. So I take a 1 over velocity dr, because r is the thing we're integrating over. And that now tells me what my integration bounds are. I'm going from r min to r max, r1 to r2. And so this velocity gets distributed. It'll cancel out with this one. It'll give you a 1 over velocity on this term. But that still leaves you with a little bit of a problem. Actually, let's, why don't we factor out that negative sign. It still leaves us with a little bit of a problem, because we've still got, I want the pin, that's what I want. It still leaves us with a little bit of a problem, because the velocity is gone from this first term, hooray, but now it's been inherited over here on gmm over v. And let's call this guy r2 to the minus 2, because that makes doing integrals a little bit easier. dr. Oh, and I need my integration bounds, r1 to r2. And so I can integrate this, right? That part is pretty straightforward. I'm going to leave a little space here for a reason. So that part is pretty straightforward. I've got a minus b times r2 minus r1. Let me double check my notes when I was working this out yesterday. Yes, that is what I get. Oh, you know what? I left off 1 over mass here. Doesn't matter all that much. It's just multiplying everybody. So we got a 1 over mass. And so this is really b over m. And then I can cancel this mass with this mass over here. So I'm glad I looked down at my notes. Yeah, that's what I got when I was working on this last night. V0 minus b over m, r2 minus r1. Okay, and so now the problem becomes doing this integral. If the v weren't there, I could do this integral. I could take this r to integrate it. That's pretty straightforward, but I don't know what this v is as a function of the position. So here's a simplification, is that we're just going to replace v with its average value. Right, so we're integrating from r1 to r2, so we're just going to replace v with its average value, which we're going to approximate as v final plus v initial divided by 2, right? That's how you take an average, simplistically. That's not really going to be the average, because it's not necessarily going to, it's definitely not going to go linearly from one to the other, but it's a decent approximation. So we've got v0 over 2. And so this integral, let's see, it'll pick up a minus sign. So we'll have a negative g capital M over v naught multiplied by 2, because we're dividing by this velocity. So the 2 goes upstairs, the v naught goes downstairs. Yep. And so then we do this integral here. And so when I take the integral of this thing, it's going to become negative, and it's going to get it's going to be multiplied by -1, because it needs to be an r to the -1. As if I take the derivative of this thing, I'll drop down a -1. There's my negative, and I'll demote the -1 to a -2. So that's the integral of r to the -2. And I don't know why I called that an R2. That is not correct. Oops, let me just make a quick little edit here. I went ahead and put in a bound there. That's not the thing I'm integrating over. Do I have that up here? No, okay. Because I need to evaluate that. I need to evaluate that from R1 to R2. And so this whole thing becomes 0 equals V naught. I'm not a fan of having minus a difference, so let's call this plus B over M R1 minus R2. I know that this quantity is negative, but I'd rather see a positive on the outside. Plus 2gm over V naught. And so this thing is going to be R2 to the minus 1 minus R1 to the minus 1. Okay? So this is now our equation 2. Right? So I've got, so after all of that calculus, I've got two equations. I've got the one equation here that gets it up to R1. Right? And I've got this equation that gets it from R1 to R2. And I've added an unknown, right? I've added one unknown of R2 equals question mark. And so I've got three unknowns. The speed it needs to leave R1 at, the value for R1 and the value for R2. I've got three unknowns, but I have two equations. I've got equation 1, and I've got the final version of equation 2. And algebra tells me that if I have three unknowns, I need three independent equations. And so what I'm asking you, dear viewer, am I missing something? Is there a physical constraint that I'm missing? I've already tried doing a conservation of energy between point 1 and point 2. Conservation of energy is that the change in the kinetic energy plus the change in the potential energy. No, I cannot write a K to save my life. I'm sure I could do it to save my life, but I can't write Ks very well. It needs to equal any work that takes energy into or out of the system. So the change in kinetic energy is the final minus the initial 1/2 m V naught squared, plus the change in the potential energy. And so that is the final negative gmm over R1 minus the initial negative gmm over, other way around, R2 R1. There we go. And that needs to equal the work done. So we've got integral of any dissipative forces, that's going to be our drag force, over the distance. So you can do the same, I'll do the same trick over here, replace V with V average, and you'll get a, this is going from R1 to R2, so you'll get a V naught over 2, a B, and then R2 minus R1. Oh, and actually this needs to be a negative because it's representing an energy loss. And so the total, the energy here needs to go negative, or needs to be lost. The change needs to be negative, that's what I'm trying to say. So the work needs to be negative. So we get a negative over here. And so on this side, we've got a negative 1/2 m V naught squared. Let's go ahead and flip these around, plus gmm over R1 minus gmm over R2. But here's the problem. This equation gives me the same information as this equation. These are not linearly independent because doing this trick, this changing the dt into dx, actually turns Newton's second law into the conservation of energy equation. It's actually kind of cool. And so this conservation of energy equation doesn't really yield any new information compared to this, because if I divide all of these folks by, what you can see is if I take this equation, let me do this in red, here we go. Because if I take the conservation of energy equation and I multiply everybody by a -2 and divide by m and divide by v naught, I end up with this equation. Because I end up with because I end up with a, come on, take me back to black, there we go. Because I end up with v naught minus 2gm, or actually that goes away, doesn't it? 2gm over v naught r2 to the -1 minus r1 to the -1 equals, let's see, that'll cancel, the v naught will cancel, the 2 will cancel, the negative will cancel. I'll have a b over m r2 minus r1. And so if you match that up, can I zoom out on this thing? Yes, I can. Good. If you match that up with, no, I cannot zoom out, it's just scrolling. Okay. Well, if you match that up with equation 2, you've got your v naught, you've got your 2gm over v naught, r2 to the -1 minus r1 to the -1, and you've got your b over m, r2 minus r1. There's a little bit of a sign difference. Why is there a sign difference? Oh, this should be a plus because I flipped those. There we go. Yeah, so you have r2 minus r1, and then if you move this over to this side, it becomes positive. Or it flips this sign, r1 minus r2. And so conservation of energy doesn't yield any new information, unfortunately. No new info. So those two are not linearly independent equations. And so, yeah, I'm a little bit stuck here. So what I'm asking you, YouTube, is there a physical constraint that I'm missing? Is there some sort of boundary condition I'm missing at either one of these? Is there something at infinity that I'm missing? Because I'm not sure that it does me a whole lot of good to set to move the having 0 speed from here out to infinity and making this the escape velocity, because then that's just bringing in one more unknown but then one more equation. So I don't think that's going to help. Then again, this is a second order differential equation, Newton's second law. And so a second order differential equation always has 2 degrees of freedom. And so I've got 3 unknowns here instead of 2 unknowns. And so it's possible that I'm mistaken about any of these. So I'm gonna do a little bit more thinking about this. I'm gonna put this part of the project on hold for right now. There are other elements of the enemy ship controls that I can work on that don't depend on this. So I'm going to work on that in the next video. But please let me know in the comments. Let me know on Twitter. Is there something I'm missing here? Is there a physical constraint I'm missing? And if there's not, if this is all there is to know about the problem, then I got to figure out a way to set one of these things. There's a few options I can go with. I could make, let's draw options over here. I could make R2 equal to some multiple of R1, or I could make R2 R1 plus some constant. So that way their relationship is fixed. That would certainly be easy to implement. I could also pick V0 to be either the escape velocity, or I could pick it to be the ship's terminal speed in a black hole free zone. There's some natural choices here, but I don't want to unnecessarily constrain the system if there's some other natural condition that I need to apply here. And of course, if I've made any mistakes in my algebra along the way, please let me know. But I've worked it out like 3 times now, and I seem to come up with the same answers. But more importantly than the algebra, I am missing an equation, because for 3 unknowns, I need 3 equations. So do let me know what you think. If there's anything I'm missing, I will make this image file available in the description below. As always, thank you so much for watching, and I will see you next time. Have a great day. Bye-bye.